And okay, so today the first speaker is Rupp, ultra-fast interpretable machine learning potential. Thank you.
Yeah, thank you. Yeah, welcome. Thanks for inviting me. It's my pleasure to be here. And what I will show next is, in some sense, going the other direction than the previous speakers. So let's take a look at that. I'll talk about a type of machine learning potential that we developed in the last 2 years. It was originated at IPAM, the Institute for Pure and Applied Mathematics. Yeah, you already heard about machine learning potentials, so I can be brief here. And we essentially, this potential will be much more similar to classical potentials, empirical potentials, and we will have a slightly different set of goals. For example, we will not try to beat the state of the art and the accuracy. Instead, we will say we want to be accurate enough for the applications we have in mind. And then we have some other goals. For example, we want to need less training data, we want to be robust, we want to be interpretable. And if time permits, I'll show 2 applications of these potentials. So the context is similar to the previous speakers. So in the right-hand side column, we want to be able to explore large chemical and material spaces. And to be able to do that, we need to be able to make accurate and precise property predictions of these materials, right? We need to be able to navigate in the spaces, but we also need to be able to predict the properties. And there are basically, in my mind, 2 approaches to this. One is a direct prediction based on some representation or approximation of the structure. So the cheminformatics approach, QSAR, QSPR. But that is a good approach, but it has the problem that if you want to predict a property for a compound, you need to have structural analogs of that compound in your training set. And if you want to explore new parts of chemical or material spaces, by definition, you don't have those. So that brings us to the alternate approach of estimating properties via simulations, atomistic simulations. And that is what I will talk about in the rest of this talk. And to be able to do that, we need good potentials. And as the previous speakers have already elucidated upon, the problem is we know the physics, we can solve the physical equation like Schrödinger's or Dirac's equation, but it takes too long if we do it accurately. So hence machine learning potentials. So I'll be brief here since we have covered that already, right? The idea is, as the sketch is supposed to show, the idea that we have a complicated function that we want to solve, like Schrödinger's equation, in a high-dimensional input space, right? Molecules and materials are complicated objects, no? With many degrees of freedom. And we cannot do all the calculations we want, for example, to run a dynamic simulation, but we can do some of them. That would be in the sketch, the red points, the training data, and we fit a flexible function, our machine learning model, to that data. That's, if we do it well, it will be close to the ground truth physical method, like density functional theory or couple cluster or quantum Monte Carlo. And we can use that fitted surrogate model to run the simulation, right? And the only reason why this works is because there is redundancy in the data, right? So the machine learning is about identifying correlations in data, right? And if you run a dynamic simulation, by definition, you will be correlated in time. If you work with a large database of molecules, let's say QM9, there will be correlation in structure, right? There needs to be some form of correlation that we can exploit. And that we do with machine learning. Let's not talk too much about this. The idea is known here. So far, so good, right? And we saw several success stories so far. So what could go wrong? Huh? We use the computer to identify correlations and exploit them. Well, this example on the left is not from atomistic potentials, but from image recognition. So apologies to those who already know this story. So there was a neural network that was trained to classify images, right? And it worked relatively well in evaluation, validation. It was performing very well. And then the researchers wanted to know which features does the neural network actually use to identify objects. For example, horses, right? Is it color? Is it shape? Is it a combination of those? And so they analyzed the network. You can do that. It's a bit of work, but you can. And they found out that the network indeed identified a correlation in the data, a very good one, namely the copyright notice at the bottom. So it turns out in that database, most of the horse images had the same copyright notice at the bottom. So the network found that correlation and was very good at predicting horse images in that database. It failed for others, of course. So right, there are a lot of stories like this. And the point is, it's good if you can interpret your model easily. This is the point I'm making here. We have, on the right, we have another example, something that was briefly addressed so far here. When you learn, so when you build a machine learning potential, the way we have seen it so far, okay, you make the assumption that the energy is a sum of atomic contributions. Okay, it's not true, but it's a good approximation. And then you represent your atomic environments using some form of representation, some set of features as a high-dimensional vector usually. Either the network learns it or you provide it to the network. And then you learn the mapping from these high-dimensional feature space to the atomic energy contributions. But I think I even have it on the next slide. Yes, sorry, I have a slide on that. So, right, you have an atom in its local environment, and you map this, for example, using a density expansion, like a smooth overlap of atomic position or atomic cluster expansion. And this is your input, and you map vectors from that high-dimensional space to your atomic energy contributions. But this requires learning a high-dimensional function. Yeah. And that is because these spaces, let's say you have a few thousand descriptors or features, then you have, this is a very high dimensional space, right? You can never even approximately cover it, right? So you can only learn the part where your data lives. And that means it's very easy to run into the problem of holes on this previous slide. So you trained your potential, you run a simulation, and then the simulation encounters a part of your input space, like a new part of phase space, that is not covered so well by your training data or not at all. And then the predictions of the model are wrong. So this is sometimes called holes in the these machine learned potential energy surfaces. And it's known, it can be fixed. Like we heard, for example, from Alexander, that you can use ensembles, but you need to be aware of this. And you cannot see them, right? Because you learn in a high dimensional space. It's not easy to visualize such a space, right? We'll come back to that. So now to the approach that I want to present today. So, well, we call them ultra-fast potentials because it sounds cool, no? But also because they're very fast. So how do they work? What did we do? We do the same idea of predicting local atomic energy contributions, simply because you need that to be able to scale linearly with the number of atoms, right? If you want to scale up to hundreds of thousands or millions of atoms, you need to have linear scaling. So we do that too. But then we don't use such a high dimensional representation. What we do is we use, lower left, we use an effective many-body expansion. So that is, we are explicitly enumerating all the neighbors of the central atom, all the pairs of neighbors, right, for 3-body terms, and so on. Triplets of neighbors for 4-body terms, like dihedral angles. And I think we will stop there because there are too many 5-body terms. But yeah, so we use explicit many-body terms. And what happens is that our machine learning method doesn't have to freeform learn this mapping from the high dimensional input space to the energy contribution, but it only learns low dimensional functions. Like it learns a pair potential, so a function of a distance. It learns a 3-body potential, so like a function of 3 distances, and for the 4-body it would be 6. So compared to the others, very low dimensional spaces. What this corresponds to is we are saying, also the advantage of the high dimensional approach is you can learn anything, any mapping. So even very fine details of the potential energy surface, right? No matter what, you have the freedom to learn that as long as you can describe the environment accurately enough. But you have the problem of the high dimensionality. Here, we are kind of imposing a constraint on the functional form of the model, right? We are saying the atomic energy contribution of that atom is a sum over 2-body terms, 3-body terms, 4-body terms. So it's like we have a much reduced model space. Of course, we pay a price for that. We cannot, with this, in principle, we cannot learn every possible mapping, but we gain a lot in robustness, for example, and interpretability, as we'll see in a moment. Okay, so that's the core idea. That is, of course, I mean, effective many-body expansions. So effective because the true function that maps atomic, so the energy is a many-body phenomenon, right? And we map it down to low-order many-body terms. That's why we say effective, right? These are, yeah, let's keep it at that. We can talk about that later. So how do we represent these functions, like a pair potential or a function of 3 distances for a triplet? Well, we use splines. Splines are well known. Splines are low-order polynomials. We use cubic B-splines. And the point about splines is that they have local support. So if we want to learn a 1D function of distance, we put a lot of splines on the one single axis, the distance, and fit their coefficients so that they give us the function that we want. And because the support of these these splines, these low-order polynomials, is finite, then it means if we evaluate this 2-body term, this one function of one variable at some point, we only need to evaluate, I think, 4 of these cubic polynomials, and that's it. So this is very, very fast, right? It's a basis set that we can evaluate with very little computational effort. Okay, and then we throw in the mix, what we throw in is how do we learn the coefficients with linear regression? That's very nice because it scales extremely well. So unlike the kernel methods, our computational effort doesn't scale with the number of training data. And unlike the neural networks, this is a well-defined convex optimization problem. We get the optimal solution, right? The training is fast. You can do it on your laptop. You don't even wait. And we add in a little bit of machine learning. For example, we regularize by the curvature. So the usual regularizer that controls the smoothness of your machine learned potential is, for example, the squared norm of your coefficient vector. But that kind of keeps all the coefficients low, which is good because you avoid large canceling coefficients or overfitting. But here for this, imagine we have a 1D potential function. The function is like this, we don't have data, and then it continues. We don't want it to go down in between. And so we regularize the curvature. The curvature should stay constant. So it just continues, basically, even if there is no data in the middle. So this turns out, you can do this curvature regularization with more complicated models, but it's more complicated. Here, it's really easy to do because those splines sit next to each other. Okay. So that's a little bit for the technical background. You can find the details in our archive preprint. Here are some results for a tungsten dataset from Gawachani et al. And on the right, it's just some phonon spectra to see, just to show that it works, basically. On the top right, we trained our ultrafast potentials with just 2-body terms, already get reasonable result. And on the bottom with 2 and 3-body terms. You can have, there's a lot more validation of this style in the preprint, including calculation of melting points and so. Basically, it works for tungsten. On the left-hand side, we see a chart where we try to demonstrate where we are with this approach on the trade-off between accuracy of prediction and computational efficiency. So on the horizontal axis, you see computational cost. On the top, in the bottom right corner is our density functional theory, in this case, reference. And the vertical axis is some form of error that takes energies and forces into account. And on the very left, you see some empirical potentials, all refitted to this data set, one exception. And on the middle of the plot, you see some of the current state-of-the-art machine learning potentials. And then in the Pareto frontier, and well, we are happy that at least at the moment, we improve on the Pareto frontier of computational efficiency and predictive accuracy. So with the 2-body parametrization, we are as fast as classical empirical potentials, which is, I think, the fastest you can do if you don't coarse grain, for example, so as long as you stay all atoms. And for the 3-body term, we are basically in a similar area of accuracy as the high-dimensional potentials, but at least 1 order of magnitude faster, even than moment tensor potentials, which is a pretty optimized implementation of that approach. Yeah, so that worked. We did get a fast potential with reasonable accuracy, so that made us happy. What about the other points? Oh yeah, right. The plots are preliminary plots, so don't take them too seriously. But what I would like to get at here is our approach has a lot fewer parameters than neural networks or kernel models. So that means we can fit these parameters, and we need a lot less data for that, right? So that's the upside. And you can see it here. For example, on the left, we have the ultrafast potentials. And on the right, we have SNAP and QSNAP, which is a bispectrum-based approach. And you see that in the beginning, for very few samples, like 10 samples, we are a lot better. That's clear because the right-hand side, the high-dimensional potential, has a lot more parameters that it needs to fit. Eventually, it will overtake us and will be more accurate because we have less parameters, right? So we can never achieve the same accuracy as the other model. So there's this trade-off, and we are on purpose on the one side of this trade-off. So this type of potential needs a lot less data to fit. But there is no free lunch. We pay with the maximum on the accuracy that we can reach. So we have a little bit of time. So let me show you some initial applications that we're building up. So this is a project about calculating thermal conductivity of materials with the ability to transfer heat, which is industrially relevant and also of basic scientific interest, right? This project is not originally for ultrafast potentials. We are working a lot with the Schnedt neural networks from Christoph Schütt that he presented before. And now we wanted to know, can we do the same with ultrafast potentials, or how far do they carry? So let me not go into the method details, but let it just be said that we use the green Kubo approach, and that approach means we look at how the atoms vibrate and how the heat flux. So we need to have long simulations for convergence, and we need to simulate large unit cells. So an ideal case for machine learning potentials. And let me skip one slide. No, okay, fine. So since we are focusing on ultrafast potentials here, we did a first test just with two-body terms to see how well we can fit this data. It's zirconia as our test system, zircon dioxide, so transition metal oxide. And you see that we get, even with a two-body potential only, we get quite reasonable energy predictions, 3 to 4 millielectron volt per atom, and quite reasonable force predictions for a simple model like that. And we are now, this encouraged us enough to now work on a 2 and 3 body terms version and see how far we can get. I mentioned interpretability. You can interpret the other models as well, but it's harder, right? For the neural networks and the kernel models, Gaussian approximation potentials, you have a lot of parameters and you have to find a way how to understand them. Here, it's pretty straightforward. For the two-body potential that I showed before, you can just plot the two-body functions and just look at them. Here we have zirconium, oxygen. So we see that for the zirconium and oxygen, it's basically what we learned from the data is just DFT-based reference data. It's just that they repulse each other. And for the zirconium oxide, we indeed have a preferred location. Directly interpretable, you immediately understand what's going on. If you have a hole here, like for example, the potential, maybe often it's a case that you don't have much reference data for atoms that are very close together. So if that's the case, then your potential can go up towards 0, but then down again. That's clearly unphysical. And here you immediately see it. You look at the plot and say, oh, look, it's unphysical. Let's not do that. Let's fix it. You can do the same with the other potentials, but it's a lot more work. So here are also some results. Different temperatures on the horizontal axis, the estimated thermal transport coefficient on the vertical axis. So this is the result of a lot of calculations and post-processing of the simulations. And you can focus on the crosses. These are experimental, so Mevrel et al. These are experimental data as a guiding reference. And then you see the green cubes and the blue diamondoids are high-dimensional machine learning potentials by others and by us, which give quite reasonable agreement with experiment. And our current only two-body term UFP is, let's say, clearly worse, but it's in the right region. And we are now looking towards adding the three-body terms, perhaps fixing the other bug or two. And let's see how far we get. Yeah. And this is a lot faster than all the other approaches that we tried. Okay, then I'm at the end of time, so I'll skip here. So we have also a project, maybe I can briefly mention it in the context of this European Center of Excellence on targeting real chemical accuracy at the exascale. The background here is there's a reference method called quantum Monte Carlo methods. And these are like a lot more expensive than DFT calculations, but potentially also more accurate. And they can be parallelized well. So they have been chosen as a guinea pig for the upcoming exascale computing architectures. And yeah, that's what this project is about. And it also has a, oh, excuse me, I'm sorry. Just tells me the time is up. So it has a niche for machine learning potentials as well. And here the challenge of data efficiency is even higher because we cannot afford that many reference calculations with DFT, right? And that is why we think that our ultrafast potentials can at least help here as a baseline potential, let's say, for delta learning. So let's keep it at that. Maybe I can show you this plot. We are studying with that, in that context, we are studying the behavior of hydrogen under pressure. And here is a model, 2 and 3 as UFP, 2 and 3 body terms. And even for this system, I mean, lots of atoms because of the pressure close by, hydrogen, the lightest element, and so on, we can still get quite decent energies and forces out of it. So we're hoping that this can be a robust baseline potential for a more sophisticated model. Oh yeah, right, and interpretability, well, if you plot, for example, the radial distribution function for the hydrogen on the left, and then you can compare with the learned 2-body potential, right? As it's 2 plus 3 body, there's only the 2-body, then you see that, for example, the maxima and the minima match reasonably well. So these are things you can easily look at with these potentials. Okay, we are working on a bunch of improvements. I'll be brief here. We are trying automatic differentiation, for example. We integrate into other packages like LAMP, so we can scale up our simulations. There's a number of tricks you can play with this type of model, like using different cutoff radii for different order terms that are less easy to do with other models. Let me skip that one. Yeah, there are some questions that we are thinking about. For example, we very much like our visualization and interpretability. For 3D terms, we plot like densities, but it's still like it could be more intuitive. And for 4-body terms, we just don't know. So that's an open topic for us. Validation beyond summary statistics like root mean squared error. No, we can. I've shown all, you might have noticed that I always show the distribution of the error, for example. We have other studies where we look at the relation of the error to the input space. But what I'm trying to say is just looking at summary statistics of energy and force error is not enough, we feel, right? Especially sometimes we see like, okay, the error improves, the predictive accuracy improves, but like derived quantities like the density of states eventually don't anymore. So we are a bit thinking of what are good ways of benchmarking and validating these models beyond RMSE. And yeah, and there's another problem with like if you get to multi-component systems with many different chemical elements, that is a challenge here because we learn all the interactions separately, and that can be a lot of interactions if you go to a high number of chemical elements. So alchemical learning is on the agenda, let's say. Okay, with that, I would like to thank my co-workers on this project and you. Thanks.
Thank you.
Thank you very much for your very nice talk. I think it relates to one of your challenges, but as a machine learning researcher, it is difficult for me to know when a potential is good enough, accurate enough. Does it have, is there a universal error threshold that is good enough, or does it depend on applications? And how do we communicate this? Or do you have a better idea of setting up a benchmark?
Yeah, that's the problem exactly. And well, if you look at the literature for the machine learning potentials, you would think there is like chemical accuracy, right? And that's a nice number to keep in mind, right? But that's it. There's no special significance really. And I do believe it depends on the application, and there is a problem, right? If you come from a different, if you're not an expert in the application, it's always hard, right? And yeah, no, that's an open problem. For example, we do have one study where we use some machine learning techniques to try and find regions of the input space where, for example, the model error is reliably low, and in other regions it has some more outliers, right? So we try to understand better where the errors come from and how they, but it's tricky and difficult. So I don't have an easy answer there. But I feel somehow, I mean, I think Simon Butts now on Twitter said that, well, if you want to evaluate how good your machine learning potential is, then run a dynamic simulation with it, right? Okay, that is true, but of course, then I think that should be part of validation. Yeah, so doing a bit more than just look at the errors, prediction errors, maybe run a simulation, see if it explodes, right? What are some derived quantities? How accurate are they? Like a melting point simulation, for example. But it's hard to set that up yourself all the time. So maybe it would be a good idea to have a benchmarking suite where you can kind of plug in your potential and it runs some of those tests for you, like it submits a dynamic simulation. I mean, that could be a potential way forward out of this dilemma, I would say.
Thank you. Thank you very much. Really interesting talk. A lot of good points. You mentioned that there is a relationship between the number of points and the number of parameters in your models. Do you test how that related in terms of this golden theorem of machine learning, the error bias decomposition?
Oh. I don't think we look explicitly at that. We do the usual like learning curves, of course, and well, we have some parameters, hyperparameters we can play with, right? For example, you normally use one cutoff radius around the atom, but we can have, because of the way the model is built, we can have like a different cutoff radius for 2-body terms, which is usually larger, and for 3-body terms, which usually we make smaller. That's something is observed from the empirical potentials people. And it directly influences, of course, computational efficiency, right? But also it may, it can also help with the efficiency of the model in terms of accuracy, right? We can control the where we place the basis functions. So like this, the low order polynomials, right, the splines. If you think about a 1D potential, we can place them regularly or irregularly, maybe where they're needed, right? How many? So these all have an influence, and we are trying to understand better the trade-offs there. And one thing that I find is underappreciated in the communities, both here and machine learning, is tuning of the hyperparameters, right? Hyperparameter optimization, I mean, it's realized that it's part of the problem, you have to solve it. Even if your method, like linear regression or kernels, even if that is a nice convex thing, the hyperparameters, so optimizing hyperparameters is still a non-convex problem, right? Not advertised so much, but yes. So I think, and that's, of course, there's a lot of work on that, but I'm not happy yet with the hyperparameter optimizers that we tried. And I think a robust way to fully automatically find good choices of the hyperparameters is important if people are supposed to use a method like this, a machine learning potential.
Thank you.
Thanks, everyone.